Hello everyone. We are here with my presentation on excitation system, transition and motor control in diesel locomotives and its POH. First, we will discuss about excitation and how its periodic overhauling is done. Later in the presentation, we will learn about transition and its POH. After completion of this unit, we should be able to understand where does excitation come from, appreciate role of excitation during locomotive operation, and understand different types of excitation systems and their principle of operation. So, what actually is excitation? An electric generator or electric motor consists of a rotor spinning in a magnetic field. The magnetic field may be produced by permanent magnets or by field coils. In the case of a machine with field coils, a current must flow in the coils to generate the field. Otherwise, no power is transferred to or from the motor. The process of generating a magnetic field by means of an electric current is called excitation. Next, we will learn about the role of excitation control in diesel locomotives. A diesel engine gives maximum fuel efficiency if it is loaded in such a way so that it develops constant HP with each throttle setting. In a diesel electric locomotive, load is the combination of traction motors and the current through them varies with their change in speed. So to keep main generator power constant, the output voltage must be varied accordingly. Excitation system controls the output voltage of the main generator to maintain constant horsepower, to limit the current at standstill condition of the locomotive, and to limit the voltage to avoid flashover at higher speed of the locomotive. For these jobs, it must respond automatically to any movement of the throttle handle, to any change in load on the generator, or to any combination of both. So, where does the excitation come from? Excitation systems can be roughly classified in two groups, internal and external. In internal system, the main generator and exciter is built to operate in such a way that, without interference of any other control device, main generator develops constant power at different load condition. In an external system, control apparatus outside the main generator and exciter is used to get these results. The whole problem is to properly vary the current in the field of main generator. This current may come from a storage battery, the generator's own armature, another DC generator, or a combination of the above. Now there are various types of excitation systems. They are A-type, B-type, C-type, D-type and E-type. In Indian Railways, locomotives accepting Type A rests were used. However, Type B and Type E were popular systems and Type E has maximum population. Now we will learn about Type E excitation system, which is the most widely used in Indian Railways. Electronics excitation system is known as E-type excitation system. In this system, a DC generator called exciter excites the main generator field. Field of exciter is fed from battery through control. The average current flowing through exciter field is controlled by a power transistor called exciter field transistor EFT working in switching mode. A magnetic amplifier called pulse width modulator controls the on period and off period of EFT on getting different input signals of engine speed, main generator voltage and main generator current. This is a block diagram of E-type loco control system consisting of diesel engine, traction alternator, auxiliary generator and exciter generator. Next is the basic block diagram of the electronics excitation system of the diesel locomotive. As discussed, the function of the excitation system is to ensure that the traction alternator or the traction generator demand matches the capability of the diesel engine in all the 8 notches. The excitation system keeps the traction generator or traction alternator horsepower demand constant over a wide variation of terminal voltage. The excitation system also ensures that the electrical elements required for the safe working of the alternator, that is, the maximum current or voltage, are suitably imposed. The excitation system controls the exciter field current, in turn controlling the exciter output, which feeds the traction generator or the traction alternator field. Thus, the traction alternator output is suitably controlled. Now, the basic components of the system are exciter generator, excitation panel, oscillator, armature current control reactor, voltage control reactor VCR, pulse width modulator PWM. Generator armature current is measured by a special reactor called armature current control reactor ACCR. Generator voltage is measured by a reactor called voltage controlled reactor or VCR. The excitation panel is a steel fabricated housing with component parts mounted on 7 plug-in type cards, which slide out of the housing for easy inspection. Three rheostats are mounted on the face of one card. One adjusts main generator characteristic and two adjust dynamic braking efforts. This is an excitation panel consisting of 7 cards. The 7 cards are 253 cards, also known as oscillator card, 186 card, reference mixer card, 187 card or miscellaneous card, 188 card or PWM card, 254 card or EFT card, 292 or 492 card, also known as VCR card, and 293 or 493 card, also known as FG card. These are the 7 excitation cards. This is card number 188 or PWM card. Now we will learn about the periodic overhauling of the excitation control panel. In Jamalpur workshop, POH of the excitation control panel and excitation cards is done in test room section. The basic steps involved in the periodic overhauling are: first, pre-inspection; second, dismantling; third, inspection stage; fourth, cleaning; fifth, testing; sixth, assembly; seventh, testing of panel with cards and ACCR. Now we will learn about transition control panel. So what is transition? Transition is the process by which the transmission of a diesel electric locomotive is brought from series wiring to parallel wiring. When in series, all current in the locomotive pass through all motors. This produces maximum low speed force in the motors, that is maximum starting torque. When in parallel, current is divided among the motors. This produces maximum high end efficiency, that is highest motor speed. Series type DC motors are used for traction purposes. This type of motor draws a high current at low speed and a low current at high speed. This is as shown in the graph. Now, what is the principle behind transition? We all know about Lange's law, which states that the direction of current induced in a conductor by a changing magnetic field due to induction is such that it creates a magnetic field that opposes the change that produced it. This electromotive force or voltage that opposes the change in current which induced it is called counter-electromotive force or back EMF. Hence, back EMF is the EMF caused by magnetic induction. As we can see from the relation, the back EMF induced is proportional to locomotive speed. So at a certain speed, the back EMF increases and becomes equal to the input current. Both these forces try to nullify each other and hence the current engine starts to decelerate. To counter this, we need to decrease the back EMF. This is achieved by transition in which the traction motor windings are changed from series to parallel at certain specific speeds. Also, as speed increases, traction motors rotate faster. This creates a resistance to current flow due to back electromotive force, which causes the magnet generator voltage to rise. As this increases, the generator can be damaged by the increased voltage. So to protect generators from their limitations, traction motor transition happens to combat this. The whole transition process is as follows. At the start, the traction motors are connected to the generator in 2S3PFF, that is, two traction motors in series and three parallel paths with full field. As the locomotive speed changes, the traction motor circuits are changed so that they draw a value of current that falls on the horsepower curve. As the train continues to accelerate, the back EMF of traction motors goes on increasing and the generator current decreases. When the operating point reaches top of the HP curve, motor fields are weakened to reduce back EMF. The operating point is now back at the bottom of the horsepower curve again. When voltage is reduced, torque remaining the same, current has to increase. As the train continues to accelerate, the back EMF of traction motors goes on increasing and the generator current decreases. It will be back at the top of horsepower curve again. This time, the motor connections are changed from series parallel to parallel. Instead of 3 paths for the generator current, there are now 6. This causes generator current to increase. The operating point is now back at the bottom of the horsepower curve again. Following slides show how the traction motor windings are changed from 2 series 3 parallel to 2 series 3 parallel shunt. In this case, shunt resistance provides an alternate path for the current to pass and hence the back EMF drops, in turn increasing the speed. Again, at a certain speed, the windings are changed to parallel and finally to parallel shunt. The whole process is summarized here. When the loco starts from standstill, all the traction motors are in series parallel. As the loco accelerates, the control system switches the combination to full parallel in so many steps to allow the motors to accelerate. At around 7-8 mph, the generator begins to take full horsepower from the engine. At 17 miles per hour, the motor fields are shunted. At 23 miles per hour, the transition takes place in which the traction motor windings are changed from series parallel to parallel, and finally at 49 miles per hour, the motor fields are again shunted. Thus, as the loco changes from series parallel shunt to full parallel, the generator output is cut, and the fuel to the engine is momentarily stopped to reduce the flashing on the switchgear and strain on the drivetrain. Shunt position is also known as shunt position is also known as weak field position, where a resistor is placed across the windings to reduce their resistance and increase the amount of current that can flow. Thank you.